Good. And once we did this, you can ask the question, right? Why do you have to start with 5? In the beginning, why not making, and then we tuned it a little bit around. Why not starting with 1 packet, and then maybe 1 and 2, and making it something like a triangle, right? So what we did there is we were talking about on the fly. On the fly was the idea, so far with all the codes we had, so go back to the full RLNC, we take all the packets, we code them over the coding matrix, we send it over. When we have all of them, we can decode. What happens with the latency? First of all, if it is a stream of packets coming in, I have to wait until all P packets are there. Until all the G packets are there from the generation. So if there's a 32 and it's a video stream with 40 millisecond interspace time, you wait a long time until all packets are there. Then you start the encoder, that takes a little bit of time, and then you send the packets, the code packets over, right? On the other side, you take them and you decode them, and then you have it. But if you look at the latency, it's taking out a long latency. Now, on the fly means, why don't I do the following? I take the first packet that comes in, and I send it to the other side. And then, when the second packet comes in, I take the first and the second, and I combine them, and send it to the other side. If the third packet comes, I take the first, the second, and the third, combine them in linear code, and send them to the other side. So it looks a little bit like the perpetual code, right? There's only one difference. What will the decoder do? What will Codo do in this case? So the first packet comes in. He looks at it. It's not even coded, right? He will give it up to the application and say, live with it. When the second packet comes in, it's a coded packet out of packet 1 and packet 2. As he has packet 1 already, he can say, oh, here's packet 2, and gives up to the higher application layer. So if you think about latency, we don't have any stopping at the encoding side. And even in the decoding side, we don't have any delay. So the packets just go through like this. Very easy. Sounds too good to be true, right? The problem is, the first time you lose a packet. Yeah? But maybe we can do there something. Let's just look at on the fly RLNC, right? We don't use this fixed corridor now. We just make something like a triangle. Very simple. Not full, just a triangle. It looks like this. Now, the number of zeros is not as good as before, right? It doesn't matter. Now, we want to try something different. We just start with the first, and then we combine them like this. So here you see what happens. If it's error-free, I send packet 1 to the other side, it goes out. Packet 2, other side goes out, because I have packet 1, and this is a linear code. I have rank 2, I can clean it up, and I get packet 2 out of it, and so on until you get packet 8. Now, as we said, too good to be true, because once you have the first error that happens over here, you will then have, you cannot decode it anymore. What we did before, we called it instantaneously decodable. That was nice, but we are losing this feature with the first error. Okay, so what we have to do then is we have to wait. You see packet 1, wait a minute. Here we could get more packets. This is what the rank is showing, right? We are increasing it, but we need more in order then to clean it up in the end. So we have a little bit gain on the latency on the top, but in the bottom it's more or less the same. And if you have a long generation and you have a lot of errors in a wireless context, for example, where coding makes a hell of a sense, you see that, yeah, it will not help so much. So the other thing is, so if you have 10% error, for example, and you just open it, you always take 1 packet more as incoming write, you will see you will fail for a while. So the question is, why the triangle? Maybe it should have a different shape. So if we know that we lose every second packet, for example, right, or every third packet, we just say, okay, we take packet 1, packet 1, packet 1, packet 2, and packet 1 and packet 2, and we are not so aggressive. What we are saying here, we're not opening our corridor so quickly. So if we can estimate the error rate, we can maybe also estimate how deep our triangle should go. The deeper we go, the more resilient we are, but on the other side, we also send more linear dependent packets. But we keep maybe the the instantaneously decodable feature. If we do it not so steep, then it might break. Right? We never send linear dependent packet by design, but we're losing the latency constraint here. So let me show you what this is. On the left, you see this corridor, this binary, right? You see what happens here? The packets he's cleaning up for a while, right? Wonderful. So again, with the higher field, this is the triangle, and we estimated it nicely. So it goes steep. So you see that there's always some way where we have to clean it up, but after a while we can clean up and we go. So suddenly, what we have here, we want coding. Why? For resilience. We want the data to get there safe on the other side. And normally, if you do resilience, you have to give up latency and you have to give up a good portion of your throughput. Now we have both, right? We have resilience and latency, but still there's a trade-off a little bit, right? Because what we do is we overshoot maybe a little bit, right? Even this is now an emulation. We say 10%. If you know the error rate is 10%, I know exactly the steepness. It will work after a while.